share the screen. Oh, we got something here. Cool, so here's Desmos. If you've used it before, it's a pretty awesome graphing program. If you've never used it before, it's just Desmos, DESMOS.com. It's really great. It does a whole lot of really cool things for you. And it's a great program to use to double check your work, especially when we get into the graphing stuff. So to begin, let's open up our packet to, I think it's 2.5, I want to say. It should look like a bunch of graphs. There should be a grid, 3 across, 4 down. And in the top left-hand corner, it just says f of x equals x cubed plus x squared minus x minus 1. That's going to be the function that we're going to be looking at for the majority of class today. And so what I'd like you to do on that first graph is plot these 3 points and then connect them as this curve, this red curve here, right? And so one thing to note, sorry, I'll highlight those again. One thing to note is that there is a point that is below where 0, -1 is. A little bit to the right and a little bit below before it curves back up and goes off to infinity. All right, so plot those 3 points and then connect it with that cubic function. And does everybody have that graphed?
Yes.
Cool. All right. So when I have Desmos projected up like this, I have the Teams meeting in the lower right-hand corner, and I can only see one set of initials at a time. So if you need more time or anything like that, just let me know by turning on your mic and letting me know. Cool. All right, so what we're going to do is work with graph transformations. You most likely have seen these in Algebra 2. If you took pre-calc in high school, you definitely saw these. We're going to actually see how these things move on the graph. So notice that I have a red curve for the original, and then this blue curve. So it's the function f of x, and then plus a. That's one of the neat things you could do with Desmos is that you can write out a function and say, hey, let f of x, this thing, this object, represent this function. And then if you notice on the left-hand column, I can then call up f of x whenever I want to, and I don't have to keep retyping everything, which is kind of nice and powerful. So we're going to take the function f of x and then add this number a to it. And then just keep track of what's happening. What does it look like a is causing this graph to do?
Increase on the y-axis?
Yep. So it's just honestly picking this thing up and moving it up in the y direction. So, just to get a sense of this thing will just keep going up. Why don't we stop it right here? And you should be able to plot those points. Yes. So for this graph, you'll want to plot these points. There's this other one over here. Plot those 3 points on the graph in the middle column, top row. All right, so where it says f of x plus a underneath it. And then for the effect, you'll want to write that it vertical shift up a units or something to that effect. You could just say up a units for the effect. And just to help make sense of why that is the case, we normally write y equals f of x. And so what you're doing is you're just adding a to every y value. And when a is a positive number and you're adding it there, your y value just goes up by this constant term a. So you're essentially just taking all your y values, adding a to it, and that's why it's just a vertical shift up by a units, graphically speaking. All right, so I'm gonna reset this back down to 0. And then we're gonna look at what happens when you do f of x minus a, where a is a positive number. So this is a case where it's like f of x minus 2 or something to that effect. Because 2 is a positive number, you're just subtracting it off. What do you think is going to happen in this case?
It'll go down.
It'll go down a units. Good. Yep. So if we just push this thing down, the purple graph is the one that is now changing. And why don't we push that down to here? All right, so that gives us several points that we can plot. And you'll want to graph this purple curve on the top row, rightmost columns graph. Oops. And notice the relationship between the original red curve and the purple curve. They look identical. It's just between all the points, there is 2 units down, right? So the point -1, 0 is on the red curve. The point -1, -2 is on the purple curve. The point 0, -1 is on the red curve. The point 0, -3 is on the purple curve. And that relationship always works. It looks like it gets kind of a lot closer the further to the right you get, but it really does stay that way, where there's 2 units between what the x values would give you. All right, so those are the 3 points that you should plot. And once that gets there, yeah. And then you just connect those with the curve. Cool, so I'm gonna bring this all the way back to 0. And then we'll look at what happens when a is on the inside of the parentheses. So we're going to look at f of x minus a. This is the second row, second columns graph that we're going to be doing. And so as a increases, we're looking at, again, f of x minus a. What is happening to the graph? Which direction is it moving?
Shifts to the right.
Shifts to the right. Good. So why don't we just park this thing right here? And here are some points that you can plot. That one's going to be kind of tricky. This one, so those are the 3 points that you can plot fairly easy. And then just swoop it together with the curve. And notice that the y values, okay, so this is at 0, -1. This is at 2, -1 now. So everything just legit got pushed 2 units to the right. And so that would be your effect, is right 2 units. Oops. So you got, again, those 3 points that you should be plotting. Ooh, overshot, there we go. Cool. So the next one we're going to take care of is the third or the rightmost column, second row, where we have f of x plus a, and a is a positive number. I'm going to switch the color on this. What color do we want? We can do blue, green, purple, orange, or black.
Purple.
Purple. Good call. That is my favorite color. Cool. All right. What do you think is going to happen here?
It's going to shift to the left.
It's going to shift to the left. Good. Yep. So this thing gets pushed over to the left. Let's say 2 units. Let me get this actually out to 2. Bam. And the points that you'll want to plot are -3, 0, -1, 0, and then -2, -1. If I can actually get that one this time. There we go. All right, so for me, I'm leaving the red curve on the screen so that we can compare and contrast. When you're graphing these things, you don't want to graph the red curve each and every time. You're only going to be graphing the one that we're actually moving, so that when you look back at this, you can see how the transformation behaved by comparing it to the one that's in the top left-hand corner to whichever one you're looking at in those boxes.
Isn't the red one called like a parent function?
Somewhat, yes. So a parent function would be something that's like x squared or square root of x. I think that those are more the parent functions. We'll just refer to this as like a reference function. But if you say parent function, I'll know exactly what you're talking about. I just don't know the formal definition of parent function. And when we were going through some graphing stuff earlier in this packet, and I just talked about how you shift things down or shift it over, this is the material that I was alluding to. All right, so once you know the shape of a particular graph, like y equals x cubed, then you automatically know how to graph y equals x cubed plus 2. It's essentially you just take your curve for x cubed, move it up 2 units, and you can graph it that way. Right, so these transformations allow you to graph functions a lot faster once you know what essentially the parent function looks like. Cool. So the effect again for that one was a units left, which now brings us to what happens to our function when we multiply by certain things. So this is going to be the third row, middle column. And the C is out front. Let's see if we can guess what's going to happen. Which direction is going to be affected when it's on the outside? Is it going to be vertical direction or horizontal direction?
I think it'll stretch like horizontal, but I don't know.
Well, let's see, right? So the first 2 that we took care of, the top row, the middle, and rightmost columns, those were outside. And which direction was affected when we added something on the outside? Which way did we go? Good. Yeah, we went vertical. And notice that the second row, the stuff was happening on the inside and it went horizontally. So with this, when we're multiplying on the outside, it's going to again be affecting the y direction. And it stretches when a is greater than 1. So notice how the x-intercepts are not changing. Because if you think about where our x-intercepts happen, that is when y is equal to 0. And if you were to take 0 and multiply it by some number, right away, it's automatically 0. So your your x-intercepts will not change in this movement. why don't we plot these points? So we have -1, 0. This time we have 0, -4, and we have 1, 0. Plot those 3 points, and notice that this thing gets stretched vertically away from the x-axis. All right, so that's what happens when C is a number that is larger than 1. I'm going to reset this, and we're going to move to the rightmost column, 3rd row down. I know that your thing says that C is between 0 and 1. If you think about what happens to a number that is larger than 1 when you take its reciprocal, where does that land you? Better yet, what is the reciprocal of 2?
1/2.
1/2. So that lands us between 0 and 1. What's the reciprocal of 100?
1/100.
1/100. Good. So notice that if C is larger than 1, when I take the reciprocal, it is now between 0 and 1. So that's why I can write 1 over C. Over here, it's different than what's on your packet, but it's the same exact thing. It's just written a little bit differently. All right, so if we're looking at C times f of x, and C is a number between 0 and 1, that's going to be the purple curve. And as we move, what is happening?
It's getting wider.
Yes, it looks like it's getting wider. The main thing to think of here is the y direction is getting affected because it's on the outside. And since the y direction is getting affected, this is almost like you put your hands at the top of the graph and at the bottom of the graph, and you start pushing it down. If you ever watch like the Instagram videos of like the hydraulic presses, it's essentially you're doing this to the graph. You're squeezing it together, which is what's causing it to look like it's pushing out. Is that okay? I know it's a perception thing. It does look like it's moving out to the sides, but that is because you're compressing it from the top and bottom.
So it reaches for infinity faster? Can you explain that again? That one was a little hard to wrap my head around.
This actually, it goes to infinity slower. So notice that the red curve, x equals r, let's say. Why does that work that way? X equals b. X equals s. Come on, just give me something that is another slider. F, D. Oh my goodness. F of x plus g. I'm going to create the slider and then get rid of any mention of that. X equals, cool. All right, so notice that as I move this vertical line across, the distance between the point on the red curve and the point on the purple curve is going to get larger, which means that this thing is going to, the red curve goes to infinity faster than the purple curve does. not by a lot, but as long as we keep moving to the right and we see what's happening, the gap between the red curve and the purple curve, when you're measuring it with the black line, is only getting larger.
Oh, so we're only adjusting the rate of change in y, not in x.
Right.
Oh, okay. Oh, yep. That's okay. Yep. I pieced it together there. Thank you.
Yep. So that whole conversation about squeezing it together is just a perception thing. Imagine, you have like something made out of Play-Doh and you put it in your palm and you push down on it. It will look like it's getting fatter, but you're really collapsing the vertical direction. For this one, again, that one's going to be kind of wonky to plot. But for this one, you'll want to plot these 3 points. This is really just negative 1/3, so kind of ballpark where that would be on the y-axis. And the way you can read that a vertical thing has happened versus a horizontal thing is that the x-intercepts have not changed at all, which means that there's something happening in the vertical direction. And this again is your rightmost column, third row down. This is where you'll want to plot the purple one. Cool. So I'm going to remove this one. And I'm going to set this back down to 1. And so we're moving to the middle column, fourth row down. And what color do we want this to be? Green? Green? Cool. We got green. All right, so this is our curve. C is on the inside, which means it's going to affect the horizontal direction. All right, if we look at the second row, this A was on the inside and that affected the horizontal direction. Same sort of thing here when you're multiplying. And if we multiplied by a number that was greater than 1 on the outside, we got a stretch. The opposite thing happens when the number's on the inside. So as C gets larger, notice how this thing is getting squished horizontally towards the y-axis. Right, so I'm going to do plot these 3 points here for the green curve. And again, just like the analogy we had earlier of compressing things from the top and bottom and it squished out to the sides, we're now taking this and squeezing it from the sides, which is going to cause it to elongate in the vertical direction.
What was the C value for this one?
The C value is 2. So this is what f of 2x would look like. When it comes to the effect for this one, again, this is the middle column, fourth row down. The effect is a horizontal shrink by a factor of C. And the way you can tell if it's a vertical or a horizontal stretch or shrink is based off of which of the intercepts have changed. Notice that this one is a horizontal shrink because the x-intercepts got closer to the y-axis, and the y-intercept did not go anywhere. So that is indicating that there is something horizontally happening to this graph. All right, I'll do this, and then reset this one all the way back to 1. And again, this is now going to be the bottom rightmost graph that we're going to be looking at. And we're looking at 1 over c. So again, this is next to the x value, which means it's a horizontal thing that's going to happen. And if we already saw a shrink, this one is going to be a stretch. So imagine you took your hands to negative infinity and positive infinity on the x-axis, and you just started pulling your graph. If you ever played with silly putty as a kid and put it down on newspaper and rubbed it so that you got the image on the newspaper, this is like if you stretched that image out. Did anybody ever do that as a kid? I'm just talking nonsense at this point. Do we know what silly putty is?
Yeah.
All right, cool. If you're really, really bored this week, go pick up some silly putty and try it out. It's kind of fun. But this is you stretching it horizontally. And again, the way you can tell is that your x-intercepts have changed while your y-intercepts have not changed at all. And the effect would be a horizontal stretch by a factor of 1 over c. All right, are we good to reset this one?
I'm good.
All right. So before we move to the last 2 graphs that we haven't touched in the first column, in that blank that's in the first column, second row, let's write down our general observations. If something is on the outside of the function, which direction is being affected? For instance, the first row and the third row. That's what I mean by the outside.
The y-axis?
The y direction. So the vertical direction is being affected. And if you look at, say, the middle column, first row, third row, you're adding a positive number or you're multiplying by something that's larger than 1. And so in a certain sense, it's doing what you intended or assume it would do when you're adding a positive number, right? Positive number should move everything up, vertically speaking. Now, when it's inside the parentheses, so it's next to the x, and that's the second row and fourth row, the direction is horizontal. And I would think of this as doing the opposite of what you assumed it should. For instance, second row, middle column, you have f of x minus a. So that would be something like f of x minus 2. And we saw that it actually moved it to the right. And we normally think of negative 2 as being in the left direction. So if you're taking little notes for yourself in that open square, I would say that outside is vertical, inside is horizontal, but opposite what you think it should be, or something to that effect. Addition and subtraction are rigid transformations. It's like you just pick this thing up and move it whichever direction you want it to. Whereas multiplication is stretching or shrinking your function. let's do the point. I don't know. What are a couple good numbers? I don't know. 2, 3. 1.5, 3. Cool. That's on our graph. Now, for the first column, the leftmost column, third row down, the negative is on the outside. So what is happening to the function if it's on the outside? Which direction is being affected?
The vertical.
The vertical, yeah. And I plotted this point down here so that we can see what's going to happen with one point. I don't know, let's do orange. I don't know, purple and orange is kind of a nice combo. So what just happened to the point, the purple point, when we switched the y to being a negative? How can we say that in sophisticated math terms? What just happened? I can plot another point too. So we have -2.
It reflected on the x-axis.
Very good. Excellent. Yep. So the two purple points are the ones we want to keep on our, that we started with on our graph. And then the orange ones are what happens after we negate the y value. And as was pointed out, that flipped or reflected our graph over the x-axis. So you don't need to plot those points. I was just using that as a means to demonstrate what happens when you have a negative in front. So again, the y direction got affected. You'll want to plot this green curve. And it really is, honest to goodness, just reflecting this thing over the x-axis. It's like there was a mirror on the x-axis and you just traced what you saw in the mirror. So a negative on the outside is a reflection over the x-axis, which affects the vertical direction. That's the thing to take away, is that it affects the vertical direction because it's on the outside. And who wants to guess what the last lower left-hand box is going to do?
Will it reflect over the y-axis?
Good. Yep. And let's just maybe keep track of one of these points. All right, so you're negating the thing on the inside, which means that you're negating the x. And notice that this purple point here went to this orange point over here. And this one might get a little messy, but essentially this purple point, when you negate the x value, goes to this orange point over here. And so it's flipping over the y-axis. And we end up getting this point, and this point that we can graph. It's like you set up a double-sided mirror on the y-axis and you just traced what you saw in that mirror. All right, do we have any questions on any of that stuff? Is the packet on Blackboard the filled in packet or the notes that we've been taking for the last month? So the filled in one, is that what you're alluding to? Gotcha. Okay. Cool. So that takes care of that whole thing about the transformations. Transformations are super useful, especially in this class, as well as when you take, or if you take Calc 1, this allows you to at least get a sense of where the function lives and what it looks like just by kind of pushing around other functions. So if you think about what we did in the last section, where we talked about the identity function, the square function, the cube function, the square root, the cubed root, now we can actually take that and just start pushing that around whichever way we want to give us other graphs based off of these transformations. I just noticed that this is actually the last section of this packet, which is really fun. Which brings up a really important topic. The first exam is going to be after the chapter 3 packet is finished. Chapter 3 packet only has 3 sections. So if I was a gambling man, I would say that our first exam is probably going to be maybe 2 weeks from today would be a safe estimate. Maybe 2 weeks from Thursday, give or take. That would just be my guess. But I'll have a more definitive answer once we start working on the chapter 3 packet, and I will give you at least a week's heads up of when the exam will be.
I have a question.
Yep.
How are we doing the test?
So you'll have to download Zoom. And once you have Zoom downloaded, what I'll do at maybe 10 to 15 minutes before the exam is supposed to start is email you the Zoom login information. What you'll have to do is have your camera on at all points in time while you're taking the exam. You'll have to have your camera pointed down to the paper that you're working on, as well as keep your hands in the screen. So that you're not kind of fumbling over here, looking at notes or anything along those lines. Again, this exam is going to be treated very much like an exam you would take in class. So no notes, no note cards, no internet to help you with answering the questions. We don't have a set date. So again, it's probably going to be 2 weeks from this Thursday. But no guarantee. I will set a firm date once I know the firm date. It really depends on how quickly we can move through the chapter 3 packet. But I will give you at least 1 week's heads up. I'm just letting you know that we're approaching it so that you can start mentally preparing for that. Everybody good? Any questions on that? I'll have more information the closer we get. I just don't want to set a date firmly in stone yet and then have to rush through material so that we can actually finish it. And I also don't want to have to keep pushing back exams. Yeah. Cool. All right. So we're just going to keep on keeping on. Let me sign in for my tablet. Hopefully we can knock out the rest of these notes today. That would be really cool. Cool. All right, so here we are. First example, suppose that somebody gives you the graph of f. Now, what we want to do is describe how to get the graph of each of the following functions after we know what the graph of f looks like. And there's certain things that we have to look for. So why don't we highlight certain things? There's something happening on the inside over here. And then we have this other thing over here. So what direction is the inside affecting? Is that vertical or horizontal?
Horizontal.
Horizontal. So there's something horizontal going on over here. And why don't we, I don't know, bring this and swoop it down here. This is on the outside, which means that something vertical is going on over here. Back to the horizontal. Is that a stretch, shrink, or just pushing left, right? Let me highlight.
Just moving left or right.
It's moving left or right. And we can tell that by the fact that it's a negative. So it's some sort of addition or subtraction, right? So is this going to move to the left or to the right?
To the right.
To the right. Good, because it's on the inside. It's opposite what our intuition says. So horizontal right, 4 units. And then over here for the vertical thing, because you're adding 3/4, does this go up or down?
Up.
Up. And again, because you're adding and it's on the outside, we have these two transformations now, and now we have to think about, does it matter the order in which we do these? That's always the important question after you write down the transformations you see. So think about this. If you took something and you moved it 4 units to the right, and then moved it, let's just approximate 1 unit up, do you land at the same spot as if you moved 1 unit up and then 4 units right? Anybody live in a city that is based off a grid? I know some people live in New York City. So if somebody said go 4 blocks east and then 1 block north, do you get to the same spot as if you went 1 block north and 4 blocks east?
No.
Yes.
Yeah, I mean, you go 4
No.
blocks one way and then 1 block up, and you do the up instead and then to the right. With decent parallel perpendicular, yes. So like New York City, not like DC or Boston or, yeah, all those other cities that are not grid. So in this case, it doesn't matter which one we do first and which one we do second, because they're opposite directions and they're not affecting each other. So I can move 4 units right and then 3/4 up. You can move 3/4 up, 4 units right. We get to the same exact spot. Everybody's happy. So order does not matter. And I'll just make a note of that. Order does not matter. All right, so notice first thing I did was I identified the direction in which the thing was happening, the horizontal or vertical. Then noticing that it's addition and subtraction indicates that it's just a rigid transformation. It's something that you pick it up, you move it, you drop it back down. Then I say how many units it goes, and after everything is laid out, you have to figure out which order in which you have to do these things. For this case, it does not matter. Why don't we try that out again? Right, so we have something inside and we have something outside. We know that the inside is horizontal and we know that the outside is vertical. Now, what is the operation on the inside telling us? You get 2x. Is that addition or multiplication?
Multiplication.
It gives us multiplication. And so is that going to be a rigid one where you just pick it up and move it? Or is this going to be you shrinking or stretching this thing? So I'll do green dot because we see that it's multiplication up here.
Compression.
It's going to be a compression. Good. Because remember, if it's on the inside, it's opposite what you think is going to happen. So this is really, you're horizontally compressing this. So we'll say shrink, or another word for it is compression. Let me actually write that so it's legible. That would be cool. And it's by a factor of 2. And then when we look at this other one, I have this minus out front. And like we saw earlier, when you have a minus, it's just picking this thing up and moving it around. So the fact that it's on the outside is vertical down because it's negative or subtraction. We have 1 unit. And then the next thing we have to do once we identify all the transformations is we have to think about, does it make a difference which ones we do first? Or which ones we do second? So in this case, imagine if you take something and you squeeze it together, and then you pick it up, or you actually push it down 1 unit, versus you pushing everything down 1 unit and then squeezing it together. Is the end result going to be the same, or is it going to be different?
The same.
It's going to be the same. Yep. So, imagine doing it with your hands. So either you squeeze and then pull it down, or you pull it down and then squeeze. It gets you into the same exact hand position. So here, the order does not matter. All right, let's do this thing again. What transformations do we see? What are some that stand out to you? Or at least give you clues to how to approach this one?
The 2f is outside of the x plus 1, so it's going to be a vertical.
Very good. So we see this right here. That's vertical. Since it's on the outside, excellent. We get a stretch. And we know exactly how it's stretching by a factor of 2. Cool. All right, that takes care of that 2. What else stands out to you? We took care of the 2 part. So the 2 is already taken care of because we have the vertical stretch by a factor of 2 coming from the fact that the 2 is on the outside, which means it's affecting the y direction, and it's multiplication, which means that it's a stretch. So it leaves us with either the 1 or the 3, which one do we want to take care of first? Oh, that's a 2. Sorry.
X plus 1 is a horizontal shift to the left.
Good. So we have this one, which is on the inside, so it's horizontal. It is opposite what we normally think. So plus 1 is to the right. Opposite of that is to the left. And it's 1 unit. And then the last one that was pointed out was the -3. And I'm running out of space, but you get the idea. All right, what direction is being affected with the -3 on the outside?
It goes down 3 units.
Down 3 units. So I'm just going to say that's vertical, then down, then we have 3 units. Ooh, all right. Here is where things get tricky. Right here and here. We have 2 things happening in the same direction. So we have to figure out which one happens first and then go from there. Right, if it's happening in opposite directions, like we saw in example 1 and example 2, there's no interactions. It doesn't matter which one you do first and which one you do second. Because remember that if you take stuff and you stretch it vertically, nothing changes with your x-intercepts. But when you push everything down 3 units, that is going to affect your x-intercepts. And likewise, if you take everything and push it down first, your x-intercepts change, and then you stretch, that's going to have a different effect than doing it the other way around. So we have to think about this, right? What do you think is going to happen first? Let's say that we take and we plug in the number 5. How would you say calculate this thing if we can actually get an honest to goodness number for f of 5 plus 1? What would be your first step in the calculation of this thing?
Add numbers in the parentheses.
Inside the parentheses, good. So we would add this together first, giving us the 6. What I'll do is I'll write that as a number 1 to keep track of that. All right, and you can use that, what we're doing right now, this thought experiment, as telling you which steps go first. So I know that we can do the horizontal one first. Because we took care of the thing inside the parentheses for the function f. And then what would we have to take care of next? Do we multiply by 2 or do you subtract by 3?
You would multiply by 2.
You would multiply by 2. So that would be your second step. And that multiply by 2 was our stretch. So that's how you can get the order there. And then once you take care of that multiplication by 2, then you just subtract 3 at the very end. All right, so that would be your third step here. This one you have to be careful about. And when it comes to the exam or the homeworks, this is probably the best way for you to approach these types of questions, is just list out all the different transformations you see, just like what we did. Once you have those down, don't forget to go back and label the order in which to do those transformations. On the exam, when I ask you to do a question like number 3, you'll get most of the credit for writing down the transformations. The order will be part of the question. So if you forget to do 1, 2, 3 and labeling it that way, you're going to lose some credit on that question. Right? Because in this case, the order does matter. Do we have any questions on that? All right, let's dive. We're done at 9:45, correct?
Yes.
Yeah. Are we okay if we cancel or head out early today?
Of course.
All right, cool. So we'll leave it there. We're just going to pick up with this on Thursday. I need to get the other class caught up to where we are right now. Good job, team. We're right on schedule. So for Thursday's class, first off, don't forget that there's homework due on Thursday. Keep an eye out. I'll be posting a new homework assignment for this section, which will be due next Tuesday. Also, make sure to print out the chapter 3 note packet. I think that should be available. If it's not available, I will be posting that later today. Just have that printed so that we can hit the ground running on Thursday. Let me just verify to see if it's out there or not. Content. All right, so I will be posting the chapter 3 packet later this afternoon. Just make sure to have that printed out and ready to go for Thursday. We'll finish this section up. There's homework. Otherwise, enjoy your afternoon, and I will see you all on Tuesday or Thursday. Yes.
Have a good day.
You too. Bye.
Thank
Thank you.